Hello, I'm Eric,
Hello, I'm Jiwan.
and today we're going to be presenting our project about generating Yu-Gi-Oh monsters. So Yu-Gi-Oh cards are very interesting. They're a trading card game by Kazuki Takahashi. What's interesting about them is what's not in them. So Pokemon cards, for example, if you look at Pokemon, no matter which color gamut you see, you can still tell stylistically that it's a Pokemon. And color-wise, just they're somewhat close to each other. Like the blues are with the blues, so on and so forth, and reds and greens and so on. But with Yu-Gi-Oh cards, you don't have that type of consistency. Not always, anyway. As you can see, you have a prism next to a warrior, next to a doll, mechanical doll, arrows, and a steam tank. There's a lot of visual complexity as far as that these things don't really go together. Plus, they have text that description-wise varies greatly from card to card. And so why focus on the GAN aspect of this? Well, there's been work done with GANs specifically for Yu-Gi-Oh cards and for cards in general. And what's interesting about like this sort of these projects on anime works, so to speak, is that there's been work done, but typically what we noticed was that even the automatic anime characters creation paper, which throws a bunch of anime faces into the data set, and even the titular like Yugano project that serves as inspiration for our project as well, they all throw a mix of data and let the models generate fake imagery. So what's interesting to us is we think, hey, what if you can get better image generation by sticking to thematically similar data? Now, what does this mean? Like, well, look at the magicians, for example. They have rings at the back. They have similar headgear, similar clothing, armory. There may be dissimilarities as well, but you can tell there's some degree of thematic consistency. So using this hypothesis, this is our first question. Can accounting for this hypothesis using it as filtering for archetypes actually amplify image generation quality? Also, will it also increase the fidelity of the actual images and the textual content instead of just producing a bunch of, instead of calling a dragon a magician, actually call a dragon by filtering for archetypes? And then will that help us get better, not just better model outputs, but help us understand the data better as well? That's our third question.
So we gathered both images and text data related to cards through their API. To accomplish this, we developed two Python scripts as illustrated below to make API calls. And to ensure data compliance, we utilize only half of the available data in accordance with fair use policies. Additionally, we uploaded our image and text data to Hugging Face and employed the load dataset function to train and test our models.
So tools known in this space are, for example, DALL-E, Stable Diffusion, Midjourney, and they make crazy, amazing images that you already know about. Like, for example, you can see that this is a Twitter account that produces Yu-Gi-Oh cards and then churns them out. And it's incredibly well done. But this isn't the focus of our work. It's simply saying, if we filter for archetypes, will we get better image and text generation? Specifically image. So for image, one of the considered metrics was FrenchNet inception distance, which measures embeddings from fake images and embeddings from real images and compares them. The more similar they are, the lower the score. Inception score was disregarded simply because it was trained on ImageNet classes, and therefore it won't that those classes don't account for anime-esque characters. And naturally, the experimental design of this project, there's a few things where we tune in each of them, epochs for images and epochs and learning rate for text, and different metrics for both. But one thing we want to highlight is that we sample a representative data set to mimic all the data that is in the distribution. And for in the case of images, just like the titular paper, like for GAN, we shrink the images from 64 to by 64. So let's just jump into the results. For the FID scores, what's crazy is that the hypothesis fell dead on its feet. You can see that the lowest FID corresponds to having used more varied data versus just using archetypical data. So it raises questions about how we set up, how we should go about layering out different archetype combinations in order to achieve better results. We also did UNet from Stable Diffusion, but computational constraints really limited us there. Anywhere you see an X is a constraint. And for the results, here's like all data and Elemental Hero 50 epochs. Like you can see that sample data somehow looks less messy than even the archetypical construct on the left. This is a little snippet from what the UNet model produced at some point, also blurry. And when we increased the resolution, frankly, we actually got better results. This was from a subset of the data, like not even the whole thing.
So moving on to our EDA results on text data, we conducted four types of analysis. So firstly, we examined frequent key terms in card titles and descriptions. Then we employed LDA topic modeling to uncover underlying themes. Additionally, we conducted POS tagging analysis to identify the most common types of words. And finally, we analyzed the sentiment distribution within card descriptions. Our findings reveal recurring terms such as dragon, dog, and beast with predominantly non-neutral tones in the card descriptions. We also experimented with a transformer-based image captioning model to enhance text generation performance. And we evaluated the quality of our generated text using the blue metric, which measures the similarity between models' generated captions and the ground truth text. So we utilized Microsoft's GIT-based model, which had already been trained on over 6 million pairs of images and text. We adjusted hyperparameters such as epochs and learning rate during our experiments. Furthermore, we conducted these experiments on specific archetypes as well as on the entire dataset. The predictions made by our GIT model on card descriptions were promising. Although the blue score was only zero point 0.2, indicating room for improvements, similar observations also were made for card titles like this.
Yeah, for example, that is not the Dark Magician's name. He's not Timeus, whatever that is. Yeah, we have a Streamlit app at the end, but lastly, conclusions. It doesn't look like singular archetype selection helps with FID scores. We might want to consider mixing them. The UNet was very computationally complex and just very like the runtimes broke very often on Google Colab. But we would love to see better results if there are any. But so far, it looks like it was following the same pattern as the GANs. For text analyses, we can see archetypical domination within the data set, meaning some categories of cards skew the results of the whole thing, bias basically. And then the blue metric and the FID metric are simply metrics. There are more things to consider, more metrics to consider that could help us understand this problem space better. This is just a snippet of what we could do. Major limitations were vicious training times, very vicious, like 1 hour to 2 hours, depending on what we are doing, pretty much across all the models. And different package conflict dependencies, like I couldn't even use a style GAN because there was a grid sampler 2D issue that was never fixed by PyTorch. And we thought about data augmentation, but maybe we should consider stuff like undersampling to help better and then augment from there. And lastly, time. And we have a repository on this. We hope we linked it with the email. And yeah, let's just jump into the app itself. So it's already running with Streamlit app. Streamlit run app. It's here in the and let's go. Let's use Blue Eyes. So the scraper runs in the background and chases out and basically scrapes the specific archetypical data. So anything that has Blue Eyes in the name will be downloaded to a folder on the back end. Also ensuring fair use compliance. Well, let's see what cards we get. I like that one a lot, not gonna lie.
Can we also see Magician?
Magician?
Uh-huh.
Oh. It's important not to click anything while this is loading. And also we have a section here where it says like generate image. That's where we use the Stability AI API. We wanted to have a little fun with it and see if it could obviously it was going to make better images than whatever we made and better. But we were pretty curious about what it will do. It does take a while. This does take a while. In fact, you can even see it running on the back end. All these downloads happening and then cleaning the data from bad images and bad actors, so to speak. And then once it's ready, I like that one.
Me too.
What do you want to generate from the Stability AI API?
You can try.
Me? You gotta give me one suggestion after me.
Mhm.
Cookie. I'm hungry. Don't blame me. Let's see. Let's see.
Mm, where is cookie?
Yeah, where's the cookie?
Let's try dog. Dog.
Dog, that'd be better. So what's happening is this is an image-to-image model. So it's using a template from the magician data set and trying to force a dog or a cookie into it. And that's cool.
Wow.
You want to sneak in one more?
No, I'm good. I'm good.
You
Can
good?
try. Cats.
I think the professor's a cat person. Maybe not. Oh, that's great. So all this to say, this is our project. At the end, you can show a data analysis and it'll pop out the wonderful text plots done by my partner G1. It does take a while to load also because it's running a lot of stuff on the back end. But yeah,
Yeah.
thank you so much for watching. This has been Eric.
Jiwon, thank you.
Thank you.